All right, so let's work through some more of those examples. So I want to start with number 4, and it's critical, pun intended. It's critical that we realize that the function they give us, and it's underlined, and it's not always going to try to emphasize this so obviously, but it says the derivative is given by this. So I don't have to do any more derivatives; it's already given. So I don't have to do any calculations. It says, well, what are those critical numbers? So it's more of a vocabulary check than anything. So critical numbers or critical values are the x values whose derivative is 0 or undefined. So if I look here, like here's my derivative, it's never undefined, at least within that polynomial, other than the two endpoints. So I want to say, okay, well, when does the derivative equal 0 then? So when does 0 equal 2x minus 1 squared times x plus 4? So that's when x equals 1/2. It's when x equals -4. And then I have my other two that are in the interval. And I notice that -4 fell outside. So I'm not going to include that. So my critical values would just be the 1/2 plus the two endpoints. So it's just 1/2 plus -2 and then plus the 5. That's it. Those are the critical numbers. And remember, critical numbers are x values. I want to stress that again. They're the x values. We don't know enough about calculus yet to go backwards. So we don't know what would have given us, like what function would have given us this derivative so that we could plug in these x values back to the normal function to figure out what's the high and the low. So we don't know that just yet. Okay, another example, again, emphasizing it's the derivative. So here's our derivative, and it's on this closed interval. So automatically, when it says critical values, I know it's -5 and 1. And what I really like is it says the original function f of x. So they're giving us the derivative to analyze something about the original function. And you're going to find that that's going to be very true throughout this, basically throughout the rest of this year. That they want you to analyze a function, but you can't see the function, but you can know something about the function, like the derivative. So when is this derivative equal to 0? Well, f prime of x equals 0 when the top is 0, because I can multiply this across. So when x squared minus 1 equals 0, which is when x minus 1, if I factor, times x plus 1 is 0. So when x is 1 or -1. And notice those both fall in that interval, and 1 was already an interval, so we don't have to include it twice. But then another thing is that when is this undefined? And so this is the first time where -4 is critical and it falls in the interval. So then it's also -4. So I get 4. I get 4 critical values. So again, this function, however, is not continuous on this closed interval, right? That's not a sign of continuity. So if that ever happens, that means you're not necessarily going to be guaranteed a max or a min. You might, but also you might not. And I think that's exactly if example 6 is coming next, this is what this is going to illustrate. So here's a function that is continuous, but it's not closed. Notice there's this open hole here. So I can't assume, then I can't use that extreme theorem and say there must be a max or a min. Now there might be, like here, right there, there's a minimum, which corresponds to the fact that the derivative is 0. So it is a critical value, but it's not guaranteed by the extrema theorem that that's going to be the absolute min. This function, believe it or not, has no maximum, because this point right here is not part of the function. So you can get everything up to that point, but you never can get there, which is so strange. It's like having a ceiling and trying to move to it forever, but never being able to touch the ceiling. This is actually called an upper bound. And it's something that you'll study even further in calculus. But an upper bound doesn't have to belong to the function, but it's clearly a boundary that everything's below it. So this actually has no maximum. So yes, there's a minimum, but there is no max. And the thing is that's okay, because we're not a closed function, right? We were continuous up to that point, but we were not closed. So there's no guarantee there's going to be both. Okay, so here, notice that is not continuous. So even though there are places like here, there's a derivative of 0, and here's undefined, and here's undefined, might be 0. Notice that this has no max or min, right? Because think about that vertical asymptote that's like centered right through. If this goes on forever, it never reaches the highest point, and this goes on forever, it never reaches a low point. So that's kind of interesting. Okay, now here, this is an open-ended interval, right? A to B, so it's not closed. It's continuous within, but it's not closed. So there's no guarantee that there's a max or a min. There might be, and actually there is. There's the max, zero derivative. Here's the min, zero derivative. But I didn't necessarily have to have it because I didn't have the two conditions that I need for that Etremea theorem. Okay, here, not continuous. So that assuming that hole is actually like the vertex, there's no max. Okay, again, that's an upper bound, and it's the least upper bound, but that definitely is not part of the function. So there's, no max. However, there is a joint min, whatever this value is, it appears it happens twice. But again, we're not violating that Etremea theorem because you're not continuous on this interval. Okay. This is one of my favorites because it's like a slide, right? So it's continuous everywhere except for the endpoints because it's an open interval. This has no max or min, right? And there's no critical value because it doesn't look like anywhere where the derivative is exactly zero. So to me, that's kind of fun. No max and no min. No max and no min. Okay. And then this one, again, is continuous within that bounded A to B, but it's an open interval. And so because this goes down and follows those two vertical asymptotes, that this is the max, but there is no minimum. So, okay. So I just, again, wanted to get you an idea. And it's nothing too complicated in terms of concept. We're familiar with maximums and we're familiar with minimums. But just to kind of add to the piece that if you want to guarantee that you have a max or a min, it'll be a critical value as long as your function is continuous on the closed interval. And then what is a critical value? It is an x value whose derivative in that function on that closed interval is either 0 or undefined. Okay, so again, I'm thinking a lot of today's, like these two videos together, are more kind of formalizing things we already knew in terms of some of these concepts in math.